let's assume we have the set of vectors x1 bar, x2 bar and x1 bar, x1 bar, x2 bar and so on, x1 bar, and such that xi bar belongs to complex domain m dimensions. Okay, the reason why I am opting for the complex domain is complex domain characterization of vectors will offer generalization over the real space where the imaginary part is going to be equal to 0. So if I have a set of vectors and let's suppose these are basis vectors. So these are basis vectors which spans certain subspace. So this is the setup, and we'd like to find out a set of vectors v1 bar, v2 bar and so on, vn bar, and which are basis vectors plus orthonormal, which spans the same subspace as the given vectors. Okay, so this is the setup. The setup is we started with a set of vectors, and each vector is n-dimensional complex vector, and those are the basis vectors which span certain space, which in fact span certain subspace, and we would like to find out the another set of basis vectors which are orthonormal in nature and which spans the same subspace as the x1 bar, x2 bar and so on, xn bar. So the bridge which fills the gap between x1 bar, x2 bar and so on, xm bar to v1 bar, v2 bar and so on, vm bar is called GS procedure. GS procedure. In other words, it is Gram-Schmidt orthogonalization. Okay. So this is a setup. We have the set of basis vectors which are not necessarily orthogonal, which are not necessarily orthonormal, and they are basis vectors. They span certain space, and we would like to find out another set of vectors which has which are again basis vectors, which spans the same subspace, and they are also orthonormal. Okay, so let's dive into this. What is orthonormality? Orthonormality. Let's discuss the orthonormality. And I have a vectors. Say I have vectors a1 bar, a2 bar, and so on, am bar. I have set of vectors, and every ai is complex domain m dimensional, and these are purely arbitrary numbers. So every ai is a complex domain m dimensional and m dimensional vector, and then the first condition is dot product of ai bar with aj bar will be equal to 0 for all I not equal to j. So this condition ensures orthogonality. In other words, this is actually ai bar Hermitian, aj bar equal to 0 for all I not equal to j. Okay. And the second condition is the same dot product ai bar aj bar will be equal to 1 for all I equal to j. In other words, this is actually norm of ai square equal to 1 for all I equal to j. So this condition ensures unit norm. Okay. If both of these two conditions are satisfied, then we call certain set of vectors as orthonormal vectors. Okay. So now the setup is clear. We would like to the set of vectors which we are aiming for, v1 bar, v2 bar and so on, vm bar, should possess orthonormality, meaning it should give us orthogonality, and it should also have a unit norm. So let's get into what is GS procedure. GS procedure. So what do we have? We have set of vectors which are x1 bar, x2 bar and so on, xm bar, where xi bar is in complex domain of dimension m. Okay, so this is what we have. and we would like to find out V1 bar, V2 bar, and so on Vm bar, where these are all orthonormal basis vectors which span the same subspace as x1 bar, x2 bar, and so on xn bar. Okay, so I'll define V1 tilde will be equals to x1 bar. Okay, and what is one of the criteria of the orthonormality is every vector that is defined in this orthonormal basis set should have unit norm. So let's make sure. So V1, I'm defining a variable which is V1 tilde, which is equal to x1 bar. So V1 bar, I'm defining V1 bar as V1 tilde divided by norm of V1 tilde. Okay. So this is V1 bar, and what is V2 bar? V2, and I'll define another V2 tilde as x2 bar minus some constant c times V1 bar. Okay, so this is how I define the V2 tilde, which is x2 bar minus some constant times V1 bar. So what is the first constraint on what is the first condition for orthonormality? There should be every vector that is being generated through this procedure, every vector V1 bar, V2 bar, and so on Vm bar, they should be orthogonal to each other, meaning that the dot product should go to 0. So what we have is this condition: V1 bar, V2 tilde, this dot product will go to 0. Okay, so this is our requirement. Now I'm asking the question, what is the value of C? What is the value of C such that the inner product V1 bar, V2 tilde will go to 0? Is the question that I'm asking. Okay, so this is the setup. So let's plug in the equations. What is V1 bar? So I'll write V1 bar as V1 bar, V2 tilde as x2 bar minus c times V1 bar, and the product equal to 0. Okay, so let's do this. So this is V1 Hermitian times x2 bar minus c times V1 bar equal to 0. This is actually V1 Hermitian x2 bar minus C V1 Hermitian V1 equal to 0. This will give us C equals to V1 Hermitian x2 bar by norm of V1 square. So if I initialize, if I plug in the C value, meaning if I define V2 tilde as x2 minus c times V1 bar, x2 bar minus c times V1 bar, where c is V1 Hermitian x2 bar by norm of V1 square, then the inner product V1 bar, V2 tilde will be equal to 0. So this implies equal to 0. So orthogonality is satisfied, but remember V2 bar is still not normalized. Okay, and if I just define V2 bar as we did for V1 bar, I'll follow the same notation. If I normalize, if I define the variable V2 bar as a normalized version of V2 tilde by V2 tilde. So this, if I define this, whatever the result that we just put, which is V1 bar net product V2 tilde, this immediately implies. So this immediately implies. In fact, it implies both the sides. V1 bar, V2 bar. Okay. So now we have successfully, we're able to successfully generate two vectors, V1 bar, V2 bar, and both are unit norm for a good reason. You can see from this equation, we know it is by construction, it is unit norm, and in inner product of V1 bar and the inner product of V1 bar and V2 bar equal to 0. So they are both unit norm and orthogonal, which makes it orthonormal. how do I extend the same thing for V3 bar is the next question. Okay, let's do it. Then the procedure in fact actually generalizes. So let's go for V3 bar. Again, straightforward. So we'll start with V3. I'll define V3 bar. Here, one important thing to notice is the basis vectors that we started. The basis vectors x1 bar, x2 bar, and so on, xm bar, they are not orthogonal. Meaning there is interdependency between these vectors. Okay, so they are not perfectly orthogonal. They can be orthogonal. There is no such restriction that they have to be orthogonal. So x1 bar, x2 bar, and so on, xm bar, they are not. They don't have to be orthogonal. So there is interdependence between these vectors, which is why we're trying to eliminate the interdependence to construct the orthonormal basis set, because our aim is to construct the orthonormal basis set, which includes orthogonality. So which is why we are trying to eliminate the interdependence between these vectors. This Gram-Schmidt procedure exactly does the same thing. In fact, the way we initialized the V2 bar, V2 tilde is we have taken x2 bar and then we have subtracted a component of V1 bar from this x2 bar. And we can straight away see that V1 bar is directly related to x1 bar. Okay. So what are we doing here in this procedure? We are actually making sure we are actually eliminating the interdependencies between these vectors to make them orthogonal, and then we are normalizing them to make them unit norm. So which actually generates the orthonormal basis sets. Okay. So which is why we have defined V2 bar in such a way that we are eliminating the effect of x1 bar on the x2 bar. Okay. So the same philosophy carry forwards for the V3 bar. Now V3 bar, I am defining V3 bar as x3 bar, and now I have two variables to take care. I have on the vector x3 bar there is a dependence on x2 bar and there is a dependence on x1 bar. So I'll define two constants, c1 c2 times V2 bar, and remember V2 is directly related to x2. So this part of the equation makes shows that we are subtracting the effect of x2 from the x3 bar, and c3 times V3 bar. So this is effect of x2 bar. So there is a problem here. Okay, this has to be c1 times v1 bar, and we are removing the effect of x1 bar, right? Now there is this has to be V3 tilde because this is not yet normalized, and now V3 bar is actually V3 tilde by norm of 3. All right. So now we have two constants to find out. Find C1 and C2 such that we have two equations to be satisfied, which are V1 bar, V3 bar should be equal to 0, and the inner product of V2 bar, V3 bar should be equal to 0. So we have two equations, two unknowns. So the same procedure carries forward. So I'll just work out for the V3 bar and then I'll write the general equation. Okay. So let's expand this. I have V1 bar x3 bar minus C2 times V2 bar minus 3. Here I am computing V1 bar and V3 tilde, and V3 bar is actually normalized version of V3 tilde. So the same result carries forward. X3 bar C2 V2 bar minus C1 0. So V1 Hermitian X3 bar minus C2 V2 bar minus C1 V1 bar equal to 0. V1 Hermitian X3 bar minus C2 V1 Hermitian V2 minus C1 V1 Hermitian V1 equal to 0. Okay, and we know that V1 and V2 are orthogonal by construction. From the previous derivation, we have chosen V1, V2 in such a way that these two are already orthogonal. So this term will go to 0. Now what I have is a clean equation again, which is this has to be C1 is actually V1 bar Hermitian x3 bar by norm of V1 square. Okay, so I have figured out the C1 part, and let's do the C2 part. For the C2 part, we have to make use of this equation, which is inner product V2 bar V3 bar is equal to 0. V2 bar, let's plug in V3 bar, which is x3 bar minus C2 V2 bar minus C1 V1 bar 0. So this will be actually V2 bar x3 bar minus C2 V2 bar minus C1 V2 bar E1 bar 0. So this will go to 0 as by construction is orthogonal. Then this will give us C2 is inner product, or I'll write in Hermitian format, V2 Hermitian x3 bar by norm of V2 square. Okay. So in general, now just we have figured out C1 and C2. I'll write a general equation for Vn. Okay. So what is the general equation for Vn? The way I define Vn is xn bar, obviously, minus, let's look at the common pattern. The common pattern is I should start from 0 and it should till go to n minus 1. Okay. Ci. Okay, let's look at the pattern. Ci Vi bar. Okay. Ci Vi bar, where Ci Vi Hermitian xn bar by Vi Hermitian square. Okay. So this is the general formula. So I'll just recap what we have done. We started with m random, not random, m deterministic vectors, and each vector is of complex m dimensional basis vectors, and they are certain basis vector which spans a certain subspace, and we wanted to find out another set of vectors which are basis vectors and which are also orthonormal, which spans the same subspace as x1 bar, x2 bar, and so on xm bar. So for that we used GS procedure, which is a shorthand notation for the Gram-Schmidt procedure, and we just defined the orthonormality. Orthonormality has two conditions. The first condition is they have to be orthogonal, meaning the inner product of two distinct vectors in the vector set should be going to 0 if index is not matching. If the index is same, then they should go to 1. This ensures the unit norm. If both of them are satisfied, we call them as an orthonormal vectors. Okay, and we wanted to find out the not just a simple basis vectors, they are orthonormal basis vectors. And the important fact that is worth remembering is these are just basis vectors, and they can have interdependencies. They are not orthogonal, they can have interdependencies. In fact, GS procedure precisely tries to eliminate the interdependencies between these vectors and make them unit norm, which gives us actually 1 bar, V2 bar, and so on, Vm bar. Okay, and the first step is actually we start with the first vector x1 bar, and then we and then v1 bar is nothing but the normalized version of x1 bar, and then for the x2 bar we try to remove the dependency on the x1 bar. Okay, so this and then we figure out the c, we figure out the constant c, which makes sure that this inner product will be going to 0. Okay, so we figure out a c, that c value is certain this expression, and the same philosophy carries forwards to the derivation of v3 bar also, because v3 now that v3 bar has two dependencies. It has dependency on v3 bar, has dependency on of course x3 bar, and it has dependency on x2 bar, and it has dependency on x1 bar. So this term is precisely trying to eliminate the dependency on x2 bar. This term is trying to eliminate the dependency on x1 bar, and so that now we have two constants, and we have two equations. So that now we have two constants and two equations, because v3 has to be orthogonal to v1, v3 has to be orthogonal to v2. Now we have two equations, two unknowns. We have solved it, and we figured out c1 bar, and we figured out c2 bar, and the same philosophy carries forward for the nth vector also, vn equal to xn bar minus. So this is a general expression for the random vector for the basis vector vn bar, which is orthonormal, is xn bar minus the minus the summation. Okay, and where ci is a constant and va bar is n-dimensional complex vector, and what is the value of this ci, and I is spanning from 0 to n minus 1. This setup just to make sure, in fact there is a problem here, this has to be I equal to 1. Okay, so this setup makes sure that xn bar does not have any dependencies from x1 to xn minus 1, and what is the value of ci? The ci values are like this. This is the value of ci. So we figured out the vectors v1 bar, v2 bar, and so on, vm bar, which are both orthogonal, which are unit norm. Okay, so that summarizes the GS procedure. That's it for this video.